We have just learned the integration by parts formula, which looks like the integral of u dv equals u times v minus the integral of voodoo. What we're going to do in the next couple of videos is look at strategies for choosing the substitution for u and the substitution for v. Category 1 involves the situation where you have a polynomial times a trig or an exponential function. Remember, we want to choose u to be a function that has an easily recognizable derivative and dv to be a function that has an easily recognizable antiderivative. In the case of the product of a polynomial function and either a trigonometric or an exponential function, we will choose u to be the polynomial function. For example, let's look at the integral of 4x plus 7 times e to the x dx. First of all, notice we can't do an ordinary u substitution that would allow us to convert this integrand completely in terms of u. But we are dealing with the product of two functions, and so integration by parts is another option for this particular problem. Again, the nature of the integrand is the product of two functions of x. One is a linear function and the other one is an exponential function. So in this case, we're going to let u represent the polynomial function 4x plus 7. Then du will be 4dx. Then we're going to let dv represent everything else, that is e to the x dx. Remember, when I'm working down the page, I'm differentiating. When I'm working up the page, I am integrating. So we're going to integrate dv to get v, and when we integrate e to the x, we learned we end up with e to the x. Again, no arbitrary constant c is necessary for integration by parts. Then our integral problem, which was the integral of 4x plus 7 times e to the x dx, can be rewritten in terms of our integration by parts formula. U times v, u is 4x plus 7, v is e to the x, minus the integral of v, which is e to the x, times du, which is 4dx. So again, I'm following the pattern as indicated by the integration by parts formula and using the substitutions that we have listed in this space right here. Now, let's see what we end up with. Remember, this first term is complete. No integration necessary here. On the second part, we have an easy to evaluate integral. That integral has been simplified from the original integral. It's something we can execute. So let's go ahead and do that. We end up with minus 4 times e to the x plus constant c. Now this result can stand to be simplified a little bit. Notice I've got two terms here. Both of them have a greatest common factor of e to the x. So let's go ahead and take the time to extract that GCF. If we take it out of the first term, a 4x plus 7 will be left behind. And if we take it out of the second term, we have a minus 4. If we simplify then what's inside those brackets, I'm just going to drop those parentheses there and combine like terms, we end up with 4x plus 3 plus c. Now again, to make sure that we build our confidence in this formula and check our answer at the same time, let's go ahead and differentiate to verify our work. So we want to find the derivative with respect to x of e to the x times 4x plus 3 plus c. Notice we're going to need the product rule because we have the product of two functions of x. So we'll take the first function times the derivative of the second plus the derivative of the first, which is just e to the x, times the second. And the derivative of c, of course, is 0. If we simplify, we have 4e to the x plus, let's factor out the e to the x. So we're going to take out our greatest common factor, e to the x. That's going to leave behind 4 plus 4x plus 3, which simplifies to e to the x times, let's go in descending order here, 4x plus 7. Now, it's in the opposite order of the factors of the original, but because multiplication is commutative, we know that we have a match here. That indicates that our antiderivative, which we obtained by integration by parts, is in fact correct. So, good job. Let's try another one. First of all, observe the nature of the integrand. We've got the product of a power function, x to the first power, and a trigonometric function, sine of 2x. An ordinary u substitution would not allow us to convert the entire integrand in terms of u. So we'll try our next approach, which is integration by parts. When you have a power function times a trig function, it works well if you let u be the polynomial or the power function. du in this case is dx. So when we rewrite this, x is going to be replaced by u. The leftovers in this integral then we will cover up with dv. So dv equals sine of 2x dx. When we integrate dv, we get v, and the integral of sine is negative cosine of 2x divided by the argument's derivative. Now again, that's kind of a review of Calc 1. Let me give you just a reminder point here. If you are differentiating a trig function where you have some multiple of the argument, then the derivative, of course, is going to be the derivative of the outside function times the derivative of the inside function. Let me get my notation right here. So if I'm differentiating. If, however, I'm integrating a sine function with a multiple of the argument, I'm going to, of course, integrate the outside function and divide by the by the argument's derivative. Okay, just a shortcut so you don't have to make a u substitution within our v substitution right here. So let's put this together with our integration by parts formula. We have x times sine of 2x dx, and we're following the pattern u times v minus the integral of voodoo, right? U times v, we can call that negative x cosine of 2x over 2, minus the integral of v, which is negative cosine of 2x over 2, times du, which is dx. Okay, so we have u times v minus the integral of v times du. At this point, everything that I write should be in terms of x. U and v help me to assimilate everything in the right order. Now take a look at our new integral that we need to evaluate. It is simpler than the product we began with in the original. If you choose your substitutions correctly, that should always be the case. You shouldn't end up with an integral that's harder or impossible to evaluate. So let's work on this integral. The double negatives will make a positive. We can move that 1/2 coefficient out in front, and now we need to integrate cosine of 2x with respect to x. The first term is good to go, no change there. The integral of cosine of 2x, remember you integrate the outside function and divide by the derivative of the argument. And this is a good opportunity for our arbitrary constant. So cleaning this up a little bit and giving you yet another option on how you express it, you can leave that constant in the denominator, or you can write it as a fraction coefficient. Either way is perfectly acceptable. So whichever way you can write it most neatly, go with that. So there is our antiderivative. Let's do check with differentiation to make sure we've done it right. So I'm going to differentiate that result with respect to x. So I'm going to have, let's do this one this way. Here's my first function. Here's my second function. So we don't have to worry about distributing the negative 1/2. So I have the first function, negative 1/2 x, times the derivative of the second. Now the derivative of cosine is negative sine, so I'm going to take that opportunity to cancel this negative out here. I'll just erase it. And don't forget, times the derivative of the inside function. So we have the first function times the derivative of the second plus the derivative of the first function, that's just negative 1/2, times the second cosine of 2x. Plus, now we're ready to differentiate 1/4 sine of 2x. The derivative of that would be constant coefficient 1/4 times the derivative of sine, which is cosine. Argument stays the same until we get to the chain rule portion. Now, let's go ahead and simplify. Looking at that first term, the 1/2 and the 2 cancel. Also, on the last term, we could reduce this a bit as well. So we have x sine of 2x minus 1/2 cosine of 2x plus 1/2 cosine of 2x. And clearly, those last two terms cancel. And we have arrived at our original integrand. It matches perfectly, which indicates that the result of our integration by parts formula is correct. So the idea in this problem, as well as the previous problem, is to recognize a pattern. Both of those integrands were the products of two functions of x. That was a power function or a polynomial function times either an exponential or a trig function. In that particular case, let u equal the power function or u equal the polynomial function, and then choose dv to be the rest, either the exponential or the trig function, and integration by parts will work beautifully.